afternoon, chairperson, moderators, presenters, and all attendants. Do you see my slide?
Yes.
I'm Kongthum Wimonsutthikul from Tricalcium University. I'd like to present to you my research, chemical and physical properties of local-made Tricalcium silicate cement for regenerative endodontics. Introduction. Regenerative endodontics is the treatment of necrotic natural fermented that aims to regenerate the ability of root development. Mostly, the material is placed directly to the tissue or in condition of some blood or some tissue fluid surrounding. So, what is the suitable material for this kind of application? Ideal properties of the materials for regenerative endodontics are quite similar with other endodontic materials, such as biocompatibility, sealing ability, very opacity, low moisture sensitivity, easy manipulation, and inexpensive. Sadly, up to date, there is no material that meets all these properties. In 1998, mineral trioxide aggregate or MTA was invented. MTA is the first generation of calcium silicate or biocemic cement. It is hydraulic, which is set with water and is unstable in moist condition. It has many benefits, such as biocompatibility, antimicrobial activity, good sealing ability, and osteoinduction. NTA product consists of powder and liquid. The powder is Portland cement with bitmous oxide as a opacifier. The liquid pipette contains water. Portland cement component in MTA mostly consists of tricalcium silicate. Portland cement is manufactured by natural raw materials, so it has some trace elements including heavy metal. Setting reaction of MTA is hydration. Calcium hydroxide from setting reaction causes high pH, which provide antimicrobial activity and high tissue formation. MTA has been used in many types of root canal treatment with successful outcome, including regeneration, apexification, perforation repair, colpotomy, and Silicate fillings. However, MTA has some significant drawbacks, such as long setting time and tooth discoloration. Portland cement is the main component in the first generation of biocemic cement. Afterward, the second generation was developed, which is Biodentine. Instead of Portland cement, the tricalcium silicate was used to avoid impurities and heavy metal in raw materials. Bismuth oxide was replaced with zirconium oxide to prevent discoloration. Calcium chloride was used to shorten the setting time. Tricalcium silicate in Biodentine has similar physical and biological properties to Portland cement. Biodentine has been used similarly to MTA. Both materials have comparable clinical outcome. Compared with MTA, Biodentine has less setting time. Moreover, Biodentine don't cause tooth discoloration. Nevertheless, the radiopacity of Biodentine is quite similar to dentine, and also the major component in bioceramic cement was changed to tricalcium silicate. This is my university Tricalcium. The development of bioceramic cement consists of three parts: the main component, accelerator, and radiopacifier. Tricalcium silicate has the same setting reaction and byproduct as Biodentine, as Portland cement in MTA. Tricalcium silicate is suitable to be the main component of bioceramic cement. To improve some properties, tricalcium silicate needs additives. Calcium chloride has been widely used as an accelerator. In addition, it also improves cement strength. Another additive is radiopacifier to provide adequate radiopacity in X-ray. Zirconium silicate or zircon is a natural mineral. Zircon can be processed to create zirconium oxide. Zircon is inert and insoluble, so it could be used as radiopacifier. In conclusion, Tricalcium silicate cement can be developed by adding calcium chloride and zircon. My research objective were to develop local-made fast-setting tricalcium silicate cement to characterize chemical composition and to investigate opacity and pH compared with biodensity. Materials and methods. First of all, I had to synthesize tricalcium silicate. Calcium carbonate and silica were mixed and fined, then mixed with zircon to create tricalcium silicate cement powder. I varied the percentage of zircon into three groups: 10%, 20%, and 30% zircon. Biodensine was used as a control. The next step was to evaluate chemical composition and particle size of tricalcium silicate cement powder. Chemical composition was characterized by XRD and XLF. To determine the concentration of calcium chloride, the amount of calcium ion from calcium chloride in biodensine liquid was identified. The result was 20% calcium chloride, so I used the same percentage for tricalcium silicate cement. The third part was physical properties testing. To prepare testing samples, biodensine specimens were mixed according to the manufacturer's instruction. Tricalcium silicate cement was prepared with the same methods, using biodensine 37 degrees Celsius with more than 90% humidity. The initial and final setting time was tested by compressive strength was evaluated by pressing machine following ISO. According to the ISO, the opacity of the samples were measured in terms of thickness of aluminum in radiograph. pH was tested following the prior study. Samples were immersed in distilled water. pH value was measured at 3 hours to 4 week period. This is our host, Langsing University. Okay, the result. XRD showed that both tricalcium silicate cement and biodensine powder have tricalcium silicate. Biodensine had zirconium oxide while tricalcium silicate cement has zircon. Burn the major elements of both cement. The small amount of trace elements were also found. Particle size of tricalcium silicate cement groups was similar, which was comparable to biodensine. Setting time: the more zircon, the longer setting time. Setting time of tricalcium silicate cement with 20% zircon was not significantly different from biodensine. Compressive strength: tricalcium silicate cement with 10% zircon showed significantly lower compressive strength than other groups. Biodensine had similar compressive strength to tricalcium silicate cement with 20 and 30% zircon. Radio opacity: tricalcium silicate cement with higher concentration of zircon exhibited higher radio opacity. Tricalcium silicate cement with 20 and 30% zircon showed more radio opacity than biodensine. In terms of pH value, varying the amount of zircon didn't affect pH values of tricalcium silicate cement. Tricalcium silicate cement exhibited higher pH than biodensine at the duration of 3 hours to 3 weeks. Discussions. Tricalcium silicate could easily be contaminated during the synthesis. Every step should be performed carefully to avoid any contamination. Trace elements found in tricalcium cement could come from impure raw materials or contamination during the synthesis. These trace elements presented in very small amounts, so they might not have any effect to the properties of the cement. Fast setting material, one of the requirements of regenerative treatment. Long setting time could delay treatment period and increase risk of solubility. Tricalcium silicate cement with 20% zircon showed fast setting time of 40 minutes. So this cement could be used in single visit treatment. The compressive strength of tricalcium silicate cement with 20 and 30% silicon were comparable to the minimum requirement of base or lining materials recommended by ISO. ISO recommends the minimum radial opacity of 3 mm of aluminum. Tricalcium silicate cement with 10% silicon or more met these requirements. Tricalcium silicate cement with 20 to 30% silicon had more radial opacity than the ODT. Therefore, these cements would provide better visual difference from dentine in radiograph. Conclusion. This is a summary of my results. Tricalcium silicate cement with 20% silicon showed similar or even better physical properties compared with biodentine. So, local-made tricalcium silicate cement with 20% silicon could be used in regenerative endodontic treatment. Further research should investigate the biocompatibility. Moreover, the cement should be tested in both animal and human prior for clinical application. Thank you for your kind attention.
Okay. Thank you very much, Dr. Kongthum, for nice presentation. Anyone have any questions? Okay. I have one question. What is the difference of synthesized tricalcium silicate cement and biodentine in the composition or properties?
Okay, the composition of biodentine mainly consists of tricalcium silicate cement, maybe 70 up to 70 to 80%. The other component of biodentine are additives such as radiopacifier, accelerator, and water-soluble polymer. So, in terms of the component, my tricalcium silicate cement is quite similar to biodentine, so the property may be the same. And my result compared to biodentine, the result is comparable.
Oh, okay. Thank you. Any questions? Okay. If there is no question, let's move to the next topic. Okay. Thank you for presentation.